Okay, welcome back. Our second talk of the morning session will be by Nikolay Gromov. He will talk about Regge trajectories in unequal force superior mills. Please, Nikolay, take it away.
Thank you very much. Thanks for this opportunity to speak. So today I will be speaking about the paper which appeared last week in collaboration with Simon and Michelangelo, King's College, Stony Brook. So it is about systematic study of Regge trajectories in unequal force superyoung mills, of course by means of integrability. And I guess on this conference I don't need to emphasize much the importance of the notion of Regge trajectories, because they are at the heart of S-matrix Bootstrap, and they control in the realistic series both the spectrum of particles and also high energy asymptotics of amplitudes. But today I will be speaking about unequal force superyoung mills, and as a conformal theory, of course there are no masses, and you have to do some notation change. So instead of masses, you consider dimensions of various operators, and instead of the spin, you consider spin, but it's key to change the notation, otherwise I will get very confused. So for this talk, S denotes spins. I know it's very controversial in the current setup, but please bear in me, is almost as good as G in any practical sense. All right, so to consider some example, the simplest trajectory is a trajectory containing, say, Kanish operator, the lightest operator in the theory. So I take L equal 2 in this case. And then what happens is that dimension, the bare one is given.
Sorry, you're in the planar limit?
Oh yeah, I am in the planar limit. Yeah. Forgot to mention. Plus gamma of S. Right, so if we start making the plot of delta as a function of, should be delta. Oh no, what happened? Okay, it's wrong gesture. So I didn't practice enough with this board. So now everything is smaller. Delta is a function of S. Then this trajectory obviously comes through when S is equal to 0 through point 2. And this is 2, this is just trace of Z square. And then when S equal to 0, that's Kanishi. And then it carries on like this. But what's important, of course, we'll consider this as an analytic function of the spin. And whereas it's not obvious how to do this analytic continuation in general, in this particular case, say at one loop, since you know the explicit result given by harmonic number of the spin, you can also make a picture of one loop correction as well. So maybe I should use different color. Let's demonstrate some skills. So this Kanish dimension is positive. This operator is protected, so gamma should vanish. And then it goes roughly like that, comes through 0. And then at this point, when S is -1, you see there is a pole. So, which means that this trajectory goes this way, and then it reappears here, carries on like that. So it has poles at all odd negative integers for the spin. So now, to consider something slightly more general, if you consider L equals 3 case, then people also computed this anomalous dimension. By the way, it's known up to many loops for this trajectory. For L equals 3, it's known up to 4 loops explicitly. And the first loop is given, okay, maybe, okay, what am I doing wrong? How to make it small again? Okay, nice. It's like massaging the screen, basically. Okay, so G square H1 of S over 2. So basically, you see it also has a pole, but this time at -2. Which suggests that in general, we should introduce variable omega, which is S plus L minus 1. And then in, for all these cases, you can see, for example, for L equal 2, that you get a perturbative expansion, which is some number times G square over omega at one loop, near omega equal to 0. And then at higher loops, this pole become more and more severe. So it become quadratic pole and so on. So in general, it is a power of this combination. And you can ask whether it resums into something interesting. Right, and actually, so it's known how to do this resummation to all orders. And this is what gives the BFKL AFKL Pomeron eigenvalue. And just to connect to the amplitude, so in the QCD, the role of omega is played. So 1 over omega would be log S, and then this is nothing but a leading log resummation of divergences in perturbation theory. All right, so let me try to go to the next page. So basically, to understand how this resums, what is good to do? Okay, it doesn't work. Just want to rotate this like this. Okay, let's do without funny tricks. So to consider S as a function of delta instead, and then this picture becomes as follows. So it's again, when delta is plus, when S is 0, this should go through 0.2. Then there is this diagonal asymptote. And then the pole appears at -1. And the actual trajectory goes like that. Where now this regime here in the middle is what is known to be a BFKL. Right, and you can see, so you can ask, for example, how fast this line approaches this horizontal line in the limit when G goes to 0, and that's what the BFKL is telling us. This leading order BFKL result is the following. So it's psi function of delta plus 1. Okay, okay, it's almost useful. So 1 minus delta over 2 psi plus 2 earlier gamma. So this I will denote as chi of delta, and this is what is the Pomeron resummation gives us. So this formula resums all these leading singularities on the previous slide. So if you revert delta in terms of S and expand near delta equal 1, this reproduces a series of the leading divergences at each loop in the diagonal trajectory. All right, so this is so-called leading order BFKL, And what is another fun fact about that is actually there's no difference between this result in like planar n equal 4 and totally unplanar QCD, because in this regime only gluons dominate, and the formula is literally the same up to redefinition, obviously, of the G. Furthermore, at the next to reading order, which is also known in QCD, and by the way, so it's like allegedly took 9 years to compute by people like Lipatov, and well, obviously they only use paper, but still quite impressive.
This is next to leading order
in G. Yeah, because there are more corrections, G to the 4 and so on, and this will give you subleading singularities on the previous slide in the anomalous dimensions. So, yeah, in general it is a series because it is, you see some function, and then you can measure how far this trajectory is from this horizontal line, right? So it will be some function of G, which you can expand.
You got this done by resumming a function of G, resumming a series of G.
Yeah, I was resumming the series of S plus 1 over G square, right? So it's precisely here. It is what is written, omega is equal to chi of delta. But then, in principle, you can also want to resum corrections, which will result in a G square delta 1 of delta, and so on. All right, so it's only known up to next to reading order, and if you look at the result in n equals 4, again, you'll see that actually the most complicated parts of the QCD result, which contain the most ugly functions, they're exactly the same. So-called maximal transcendentality principle, which gives you identity between n equals 4. So n equals 4 always contains uniform transcendentality part, the highest transcendentality part of the QCD result. Then in the next to reading order, it is known in n equals 4 from my paper with Fyodor. And in principle, it gives prediction for QCD, but you can extrapolate how much time it may take. So another problem, though, is also that in QCD, it becomes scheme-dependent quantity, like beta function and other things become more dodgy. But in any scheme which is not crazy, you still expect that the maximal transcendentality piece is well-defined, right? And this should be given by n equals 4 result. So basically, the question I want to ask today is like, what is generalization of that for general L? Right, and today for general L, what I'm going to show that we are able to compute next to leading order. Actually, it continues L over 2 times. That's one thing. And furthermore, we'll see that this n, which is order in G square, actually is a product of 2 smaller n's, because we'll see that expansion actually goes in linear G rather than quadratic G square, as anyone sane would expect. All right, so how are we going to achieve that? So for that, we'll have to use, so any questions about this part? We'll have to use integrability. So just to briefly tell, to motivate our main construction. All right, so integrability, right? So go back to school. What we know about integrability, if you have a motion in a spherical symmetric field, then you know that there are nice spherical coordinates, because then your function separates into one-dimensional terms. right? That's, in a nutshell, integrability. Now for the string, string wave function is a, or n equals 4, is a functional of the string configuration, right? So it has infinitely many degrees of freedom, but it's not a big deal, because we just need to take an infinite product. And now, what was psi is traditionally denoted by q. So in some specially chosen coordinates, you can hope this happens, where A is some kind of polarizations, encoding PSU 2,2/4 symmetry. All right, so what are these Qs, right? So these Qs are actually very well defined at the moment, even though it looks a bit mysterious. We may not really know how to do this transformation into these special coordinates, but we know these building blocks. So, and there are quite a few. So there are 2 to the 8 Q functions. But the good news is that there are only 4 plus 4, which we actually care about. Right, so why do we need 4 plus 4? And we have special notation for them. We have qi of u, where I goes from 1 to 4, and pa of u. So we denote the q function by p for historical reasons. And roughly speaking, so each set of these q's is responsible for its own subgroup, bosonic subgroup of the full symmetry, so that the first set kind of lives in ADS and another one lives in S5. And so this PZ encodes R symmetry charges, and this encodes conformal charges, right? And then for today, so it will be important to point out that kind of this I index is roughly a SU4 index, but the choice of concrete Qs is fixed, so you can't really rotate them because we diagonalized all the charges in a sense. So they're fixed by the asymptotics, which correspond to the eigenvalue of the corresponding Cartan charge. Right, so I recall S as J, the spin, right? Just to avoid any confusion. And S orthogonal, in general, you can also have spin in orthogonal direction, which we will not consider today. And for example, Q2 is something like delta minus S minus delta orthogonal, and so on. So the choice of these Qs is fixed by the asymptotics, and also PA kind of behave as U to the L, where L is the R charge of those operators. All right, so that's the zoo of the Q functions, but the question is how do we actually compute those Q functions, right? If you want to find wave function and so on, how do we do that? So the equation can be motivated by Schrödinger equation. Right, so Schrödinger equation, as you know, has 2 solutions. So normally, we only care about one of them, but let's be more democratic because we are in a free world, right? So let's consider 2 of them. And then what we know that as a consequence of the Schrödinger equation, they satisfy the Wronskian identity. And now you can try to play the following game. Instead of imposing Schrödinger equation, you can say, let's assume there are 2 functions which satisfy Wronskian identity. And if on top of that you add some analyticity information, say for harmonic oscillator, if you say it's like e to the minus x squared times a polynomial, and also say something about psi2, then in principle this contains enough information to as much information as it was in the Schrödinger equation itself. So that's roughly the approach we take for n equals 4. So instead of the Wronskian identities, we just have to replace them by some kind of super Wronskian. And just to give you some example, this one of them looks like that. So P is a function of U, and then instead of derivatives, you have to change derivatives by the function by the finite differences. So and then you find identities like that. So in principle, this should be upper index, but let me not go into this detail. And all you need is actually a complete set of the Wronskians contains 3 more identities which are not more complicated than those. Right, so there are some functional identities which these P's and Q's have to satisfy. So there are 4 unrelated, well, 4 independent functional relations, which are totally encoded in PSU 2,2/4. So if you want, like, there's a Yangian symmetry of n equals 4, which results in those functional relations. And now, as I said, obviously this is not enough to find the spectrum of harmonic oscillator. You have to say something about analyticity. All right, and analyticity, you should try to be minimalistic, right? So which kind of information we want to encode into the analytic properties? So there is one parameter which we care about, is the Toft coupling. So it should appear as some feature of this analytic properties, and the most natural way is to introduce a cut, and you can choose it up to rescaling to go from -2G to 2G. At the same time, so this would be the analytic property of PA, but for QI, you obviously, it would be inconsistent to impose this analyticity condition because it should have non-trivial monodromy at infinity, because asymptotics of Q contain, for example, anomalous dimensions. So there should be a cut going through infinity, so minimalistic choice, again, is like this. Right? And I hope to connect again with its matrix Bootstrap here, because this is something which may look familiar to you if you replace it by M square, right? This may make you happier. So, okay, that's very bootstrappy type of problem now. So you have to solve these 4 functional relations such that these 2 conditions are satisfied, right? And maybe I should actually add, I already said that you have to impose this polynomial asymptotics when you go to infinity in both ways. Yeah? Yeah, there's square root in this case, but for example, in ADS3 case, we found that it's too much to ask for square roots, and you have to assume more general. Well, basically, well, if you want the physical principle, it's kind of related to whether there are some massless modes in the mirror theory and stuff like that. So it's yes. Yeah. So as I said, so this PAs, they just U to the L, roughly speaking, plus minus L, and QIs, they behave as U to the delta plus minus S. So they all power-like. I don't know. I said polynomial. Right? It's not really polynomial. Power-like. Power. Sorry? That? Well, I mean, so obviously I'm not explaining here the whole historical path of how we arrived to this equations. So this took like, I don't know, 15 years for the big community. So it's really a shortcut. But I just trying to tell you that it's quite natural and probably way more natural and simple than any intermediate step in the derivation. So I don't want you to really suffer from all this, you know. But that's a good question. So how do we know that? And we'll see that actually it's not always true. Because, so the conjecture is now that if you manage to find solution to this set of A and B, consistent solution between functional equation which has this analytic properties, then it will be in one-to-one correspondence with local primaries operators. Well, for protected operators, it become a bit simpler because both in P and Q is 0 essentially for protected. All right, and then we also know generalization of this for ABGM. And as I mentioned recently, we also put forward conjecture for ADS3 times S3 times S4. Then you can also do all the gamma beta deformations. For in particular, you can totally kill supersymmetry by going into extreme fishnet. Well, sadly also kill unitarity. So let's not mention this too much. And you can also do non-local observables such as CASP, so which was has this wrong notation phi here. No, it was actually theta, right? Which is wrong. Anyway, so I introduced another wrong notation. So you can also do CASPs and with insertions and so on. Yeah. Yes. No, so you see there are 4 P's and 4 Q's, right? Set of Q functions is actually finite. There's 8 of them, the main ones. Then the product indeed goes, but you just pick different of them polarizations, right? Yeah, the correspondence is the following, that solve A and B, you'll find isolated solutions, and each of them correspond to a primary operator. Well, that's just for motivation. So what becomes Schrödinger equation is more like Baxter equation for spin chains, the closest analog. So there is a bit more complex than Schrödinger because potential itself is self-consistently dependent on the state. But otherwise, the philosophy is quite similar. Yeah, that's just for motivation, like how we would be solving Schrödinger, like harmonic oscillator in the way we solve n equals 4. It would be a slightly weird way. Instead of solving Schrödinger straight away, we would impose Wronskian plus some polynomiality of these Qs instead. All right. So now you see, so we are slightly in trouble because in order to find the Regge trajectory, we need to actually transform analytical continuum spin. And so naturally, as I'm sure Peter explained to you several times on the previous events, this become a light ray non-local operator. So basically this power S become non-integer, which means that instead of local, it becomes some light-like Wilson line connecting this operator. So you get some something like that in, you know, which x plus, let's say, direction. Right, so this is a clearly not very local operator, so we can't do that. However, if we slightly relax the rule of the game, we'll find that the previous set of equation is actually slightly, well, twice over-determined. So actually, instead of imposing that all Q functions, they have this asymptotic behavior, so it's power. When U goes to infinity, because you see there are 2 infinities for Q functions. So instead of imposing it for all 4 of them, it's enough to just impose for Q1 and Q3. And as I said, so in principle, choice is fixed of what is Q1 and what is Q3. So and then you don't care what happens with other Qs asymptotically. So you just impose, they have shortcut, and you can still choose that it is a power here, but actually it's not critical, and here is whatever. Right? And then if you relax this condition, then you'll find that S is no longer integer is allowed. Okay, and it's grammatically wrong, but you see what I mean. Okay, so, well, we need to run ChatGPT to fix the grammar here. But so you can now have non-integer spin if you relax this bound here on Q4 and Q3. But it's still, if you pick S to be integer, you impose that, automatically you'll find this is power-like. So, and it's just enough to impose those, and then what you get is what you get. So in principle, for non-integer spin, you'll find a new type of asymptotics, which 2 pi u times u to some power. That's how it generalizes. All right, and after that, you can do many things. In particular, you can solve numerically those equations. And actually, for this particular observable, we went a bit desperate at some point and computed 60, actually, I think 70 digits. Depends how you count them. And so you get the whole asymptotics for some finite, the whole trajectory for finite and G, like that. So it's in my paper with Fedor again. All right, so in principle, we have this infinite set of options of what to do, because we have numerically this system totally under control. I don't know how much time is left. Okay, good. Under control, however, if we go into high else, then there are infinitely many trajectories. Right? And then, even if you have 70-digit precision, if you have infinitely many trajectories, this is not good enough, so you need some analytic control over the situation. Even though I should say Michelangelo did a really great work by computing most of these trajectories numerically. Yes? Say again? Well, G is finite, yes. So then you can numerically expand it at coupling and get like next to next to next numerical numbers with high precision. But it's important to have analytic result because maximal transcendentality part which you're comparing. All right, so we need analytic control. So okay, so what happens when G goes to 0? It looks like not much it happens. So these 2 branch points, they merge together. So it's nice for P because P essentially become a polynomial, or maybe it's getting a pole in the middle. But for example, you see no indications that there are these 2 different regimes on like for diagonal, for local operators, or whether you hit a horizontal line. So nothing kind of special about different regimes in this trajectory. So you see, if you here, you approach diagonal trajectory, but if your value of delta is between ±1, then your system should tell you that the limit is S minus 1. So what's the difference? So, all right, so now, so first, for local operators, what we can hope for, right, in terms of analytic control, what gives a nice analytic control for local operators is Bethe-Baxter set of equations, which are valid up to the order to the L plus 4, roughly speaking. And they're just, so they're much simpler than the whole quantum spectral curve. And this is what is also known as ABA. And now what I will present now, so our result is asymptotic. So ABA goes for asymptotic beta ansatz, and what I present is asymptotic Baxter Bethe ansatz. To show that some of the equations, they still remain to be non-compact, which can be abbreviated as ABBA or ABBA. And like, of course, the reason for this abbreviation is clear from the name. That's the main reason. But also one of my collaborators is Swedish, and he thought it would, in the future, increase his chances of securing some local Swedish grants, maybe a Nobel Prize at some point, which actually turns out to be correct. Well, not Nobel Prize, but he did get recently. But maybe another reason we keep this abbreviation slightly silly to kind of push more serious people if they want to use our result to instead, like in the case of Bethe, use the abbreviation coming from our names, of course. You know, there are many reasons to call it like that. All right, so what's the difference between them? So basically, this one is for diagonal trajectories for some points on them. And this one is for horizontal trajectories where BFKL takes place. So the main simplification is, comes from the following equation, which is like a consequence of all I said above, but in a non-trivial way. So if you take a Q function and analytically continue it under the cut, then you will find that the analytic continuation can be written again as a linear combination of Qs with some simple matrix omega. So it's some monodromy. And then, so for diagonal trajectories for ABA, the simplification comes from the following fact that omega 4,3 out of all of them is huge. And why is it nice? Because then you get essentially Q whatever 4 analytically continued equal to some coefficient, which is just 4,3, and then you only have Q3 in the right-hand side. Right, so which reduces the whole like complicated matrix Riemann-Hilbert problem into the usual linear Riemann-Hilbert problem, which you can now solve analytically, right? So this is just the key for the simplification. Then eventually you start from this corner, and then you start writing down equation, you simplify all these Qs, and eventually you're able to write all Q functions in an explicit, simple way in terms of roots of some functions. So for that, I need to introduce similar equation for, for P. So for P, there is a similar equation that if you analytically continue, you get some monodromy mu times PB. And then what plays a crucial role is the zeros of this function mu1, 2, because what happens is that they become the rapidities of the magnons of this spin chain by the Bethe-Baxter, satisfying the dispersion relation 1 over I, so x plus x k minus, where x is a Zhukovsky map. And energy is 2ij, 1 over x k plus, 1 over x k minus. Right, so basically what happens, you find zeros of mu1, 2, and then you can compute both momentum and energy, which is the anomalous dimension of your state, just by plugging into this formula and computing the sum. So this also results into this famous dispersion relation. Okay. Ek 1 minus 16g squared pi over 2, right? Which you can actually derive by diagrams, and this was done like around 20 years ago. So you can find the dispersion relation just by considering magnons, which are flip of some scalar, some defect in the scalar c of z to the l. So that's what happens in the Beiser-Tiden-Staudacher equation. This is the simplification. Omega is huge. Then you get a linear Riemann-Hilbert problem, and then you immediately get to the physical things such as dispersion relation of the magnons. So now, in our case, for the horizontal trajectories, what we found, well, it's mostly first observed numerically, but now obviously it's quite clear from self-consistency, is that instead of omega 4,3, just omega 4,2. And it is suppressed this way. And then there are some differences at the level of the magnons. So now magnons, instead of being roots away from the cut of mu, they become roots on the cut. So, okay, now it's becoming a bit ruggedy. So you have mu, and you have some magnon sitting on the cut itself. Let's denote by zk. And then you find momentum is 1 over I log z k square. And like elementary quant of this variable omega is ij zk minus 1 over zk. All right, so basically you see instead of this plus minuses, which actually I didn't define properly, so these are shifts by I over 2. Instead of this plus minuses, you get z to be 1 over z. All right, and this is actually, what does it mean? It means that this dispersion relation become massless dispersion relation. So omega k is something like 2g sine of p k over 2. All right, and that's already, you see from there the linear dependence on g appearing, right? So before, in Beiser-Tiden-Staudacher, everything would depend on g squared. But now, essentially, this is the limit where you neglect this 1. And so you take the square root of dispersion and get linear terms. Okay, I didn't know you can do that. Okay, that's interesting. So, the message is the following. I don't want to kill you with too much technical details. But once you know the zk's, which are zeros of this monodromy of p, all p's, q's can be computed. The same way as for Beiser-Tiden-Staudacher, you can take this magnon momenta and build all p and q's in terms of them. So just to give you one example so you get some feeling what is going on. So for P is particularly simple. So you get this asymptotic. Again, I have to introduce properly this map, the Zhukovsky map, where sigma is an analog of Beiser-Tiden-Staudacher dressing phase, if you know what I mean, but for the massless case. So what we found from just solving this Riemann-Hilbert problem is a slightly different dressing phase. Which is very similar. U of x, U of y, divided by complex conjugate. All right. So all P's and Q's now can be written in terms of this zeros of μ1, 2, which we denoted by z. And that's an example. Now, how do we find this? And that's basically what the main equation is about. That's the equation which is very reminiscent of the beta ansatz. So let me, the last formula, hopefully, which is a bit long. So again, so this is like e to the I pi l in the normal beta ansatz, and the right-hand side contains something like scattering matrix, which we bootstrapped by this procedure. So it contains this part, which is analog of the Beiser-Tiden-Staudacher, but in this special case. So it is not actually Beiser-Tiden-Staudacher, but a slight modification. And then you have some factors of gammas. So which is just gamma of delta plus I theta k, I theta l over the complex conjugate. So this theta is over g is just z plus 1 over z. All right, so what you see, so we found some algebraic equation for the z's, where on the right-hand side you have all this Argo gamma functions and this beautiful new type of dressing phase. And this, in principle, is valid up to a high order NL. So let me now, okay, actually, this, oh no, unfortunately, that's the end of it. I can go here. All right. Right, so now, if we solve ABA, then in principle you can get the expansion of omega up to g to the power L plus 1. And just to give you some example, actually what you get is the following. For the first two terms, you can write on the blackboard easily. So for general L, the general states like that, plus and 1 interchange with N2. So that's, you see the linear term in G appearing, minus 16G square. So this is chi, I remind you, is a Pomeroy eigenvalue. And then you have sine square pi and 1 over L plus 2 over L plus 2 plus and 1 interchanged with N2. Right, but in principle, in general, this goes up to G to the L plus 1 terms, but they become in a bit bulky. Right, so what are the N1 and 2? So actually you can, oh no, okay, I think it's gone now. Come back. Okay. So what are these ends? Actually, you see, at weak coupling, if you send G strictly to 0, then the right-hand side actually disappears. All these factors on the right-hand side, they become 1. So you just get Z is to be roughly a root of unity. So these ends, they just parameterize which root of unity you have to pick. No, don't do that, sorry. Getting. So this N is going, so it's an integer which goes from 1 to L plus 1. With an additional condition that the sum should be an even number. All right, so now we can, for example, count how many states there are, right? For example, if we take L equal 2, then the only option is N1 equal 1, N2 equals 3. And then if you plug into this formula, you get omega is equal to 0 times G plus G squared times chi of delta. And that's exactly like QCD Pomeron. Now for L equals 3, you already get 2 states. So it's 1, 3, or another option 2, 4. And you get the following formula, plus minus 2G. So of course, even though it's a linear in G, you see this Lagrangian only knows about G squared, right? So G to minus G should be a symmetry of the theory, which would map one state to another. So that's why they're related just by G to minus G. And then minus plus 2 pi cube over 3 G cube 24 7, you know, zeta 3 over 6 plus zeta 2 kind of chi G to the 4. All right, so we get this generalization of the Pomeron for this trajectory, which we now know analytically is up to G to the 4. And then you can carry on, and for example, for L equals 30, let me just write those states explicitly. So you get 225 states. And we can compute first 31 terms. All right, so in the paper we have a picture of all the states together, just to indicate the dominance, kind of. All right, so any question about that? So now, the last thing, how much time do you have? 5? Oh. Okay, let's not do that still, right? Let's behave. So let's see how whether it matches any known results. For example, obviously this linear term in G is quite insane, as you can imagine, right? So if you try to compute any Feynman diagram, of course it will come with a factor G squared. So there's still we don't have any clear understanding on how on the Earth one can get order G. So there are, of course, some examples in some non-unitary theories where you can get any power of the coupling due to, but for that you need to have mixing matrix which is not diagonalizable, and then, okay, anything could happen. But once it's diagonalizable, in principle it should go in the same power set as each element of the mixing matrix which comes from diagrams. So that's a big challenge to understand where these linear terms come from. So you can actually like silently suspect maybe it's a total nonsense, right? So that's why I propose to run this test. All right, so let's take L equals 3, and we found two trajectories, right? So we found, which I wrote on the previous slide. One of them is a positive linear term, and another has negative linear term, but they're both divergent at plus minus 1 in delta because they're built out of this polygammas. So and then the question is, how does this merge with one single diagonal trajectory? Right, so we have two trajectories in the middle and only one to the left. So I mean, if you look into the numerics, actually it's not that insane, because what happens is the following. If you zoom next to this point, then you find the following. So the upper trajectory goes like that. That's the diagonal asymptotics. And then next trajectory flips from negative linear term to positive, and then the analytic continuation of the diagonal trajectory become -1. So how can we describe that? So let's indeed zoom into this corner. By that I mean let's introduce new variables which are convenient for this corner. So I rescale omega and delta to go closer to this regime. And then that's where we should be able to describe some picture like that. So obviously it is some cubic curve, right, at the leading order in G, at least. So what we expect is that, so there are three solutions, should come from some simple equation like that. Where all these A, B, C, D, they should be they should be essentially polynomials in delta. Right, if we want to glue together these two regimes, this should be the curve which we call branching curve. So now, how do we fix this ABC, right? So in principle, you can take whatever we want, but here we are constrained by the data coming from ABA, from ABBA. So ABBA is here. So if you go far away from this singularities, then that's the regime where, where delta is of order 1. We are far from the pole, and then we can just take the result from the previous slide, and we find that delta equal to 1 plus omega. No, it's not what I want to write. And you find that there are these two trajectories which should behave plus -2, minus 8 over d, plus 96 over d cubed, plus d to the 4. So what you do, just literally plug this redefinition into all these formulas on the previous slide, into the sporty gammas, and expand when g go to 0. And then you find this expansion. So what it tells you that this cubic equation, which obviously no one wants to write down explicitly solution of a cubic equation. In Mathematica, you probably keep semicolon at the end. But if you expand at large D, what it should, two solutions should have this asymptotics. And that's actually over-defining set of equations for ABCD, which give omega cube minus d omega square minus 20 omega plus 4d equal to 0. And now you see it's actually linear equation in D, right? So why linear? Because actually this is what will give us this diagonal trajectory. If you solve for D now, delta equal to 1 plus omega, and restore the initial variables, then you find this omega. Oh, sorry, this I switched to L equal 4. Find minus 16 g square whatever, some numbers, 64, g to the 4 over omega square, plus also g6 and g8. Actually, it should be omega square, just omega to the 4. Anyway. So which one border I was told. So you find that, and then you go to this paper of Beccaria, or another paper appeared at the same time, like 10 years ago, of Lipatov and Staudacher with collaborators. And you look at the expansion of the for-loop anomalous dimensions for this trajectory for L equals 3, you'll find exactly the same coefficient, you see. So that's a super non-trivial test that this is, of course, correct. Well, as well, we also have, obviously, numerical tests as well. But so finally, you can also see by using the data in this Abba regime, we were able to reconstruct this Gruen, the branching curve, as we call it. So you can repeat the same exercise for any L. This time you get some fourth order, no, not fourth, fifth order curve. And then from there you can find the divergences. So this curve, you see, it predicts all the leading divergences of diagonal trajectories, but it also actually predicts all the leading divergences in the BFKL regime. But anyway, so it predicts all the leading divergences. And what you find for L equal 4 is 4g squared, 3 plus minus square root of 5 over omega. And then, like, for anyone who would like doing integrability in n equals 4, this number, of course, is a, well, I mean, for some people is a golden ratio almost, right? But for people in n equal, are we being abducted by aliens, or what's going on? Okay, so we're in safety. Right, so for anyone in integrability, this number is clearly very familiar. This is nothing but the anomalous dimension of the local operator of this type. So there are two primary operators with spin 2, which has this, this number. So that looks a bit weird, but then we continued up to L11, and each time we found the same relation, that number of poles will increase with L. So there will be more and more diagonal trajectories, but for each of them, we will find the following relation, that is 32 minus 2 anomalous dimension Pn. So where Pn is just the leading pole over omega. Right? So what is gamma n? Gamma n is now the anomalous dimension of all operators of this type. So the number of these operators exactly matches the number of trajectories which decide to turn into the first BFK singularity. So you have now many trajectories, and those which turn here, the number of them matches our counting, but as well it also matches the number of primary operators of spin 2. Like, it's like totally insane, this relation, and there is no clue why this should hold, because that's something about behavior of the light ray operator at the point where it becomes maximally non-local, and anomalous dimensions of the most local operators possible. So that is another mystery. And let me just go to the conclusions. Are there any questions? So, I mean, so first, like, what we obtained lots of new CFT data, very explicit one, which one can play analytically with, but it's still unclear what's the meaning of these massless modes and how these linear terms in G could appear if you start computing the things in perturbation theory. So that's, I guess, the task for Peter to some extent, to explain me in the next year how that's possible. Then another question is the spin chain. So we didn't actually find any spin chain as such. What we found is a beta ansatz, right? So the question is, what is the spin chain which it diagonalizes? But then you see, so there are certain similarities with what people found in the ADS3 case, and there also it's not really known what the spin chain is because there is no actual CFT which people know to be dual to this ADS3, S3, T4, Ramon system. Then finally, we are currently working on generalizing this result. So currently I only describe the leading horizontal trajectory, but in general, you find that there are lots of shades, and that's so there are many subleading trajectories which correspond to higher twist operators, as well as there are also many subleading trajectories in to BFK1. And all of them, in principle, they should have the same feature that we should be able to solve it analytically to some extent, or write a closed system of equations similar to Bezier-Tiden-Staudacher, but with some extra massless particles. So, and yeah, and certain inspiration which we learned from this solution will be also useful for ADS3 quantum spectral curve, and that's the work which is currently in progress. And I'm now concluding my talk. Thank you.
So are there any questions for Nikolay? Maybe I have just one. You didn't want to mention, but what happens in the fishnet?
Oh, in fishnet. I think actually Peter knows what happens in fishnet somehow. But there in principle for lens 2, there is an analytic formula for the whole trajectory.
Yeah.
So the question whether there is similar simplification in this regime, yeah, it's a good question. Yeah. There should be, because you can twist all the system and then take the infinite twist deformation limit. And then you'll find all this non-trivial S matrices like Basso and Kazakov and Zhao, Cayetano found for the fishnet. There should be similar. The addition of massless particles.
Any more questions? Okay, if there are no more questions, let's thank Nikolay again.